Hello friends, welcome back in the Rose project. Student, I am Dattatreya Jadhav from Sadguru Gadge Maharaj College Karad, which is a branch of Rayat Shikshan Sanstha. This lecture is conducted for Rayat Online School Education project, that is our Rose project. Students, it's our third lecture on linear programming problem. So today we are going to solve linear programming problem. Linear programming problems is an optimization technique used in different fields such as management, planning, productions, transportations, etc. It is developed during the Second World War to optimize the utilization of limited resources to get maximum returns. Linear programming is used to minimize the cost of production and maximizing the profit. These problems are related to efficient use of limited resources like raw materials, manpower, availability of machine, time and cost of a material and so on. Linear programming is mathematical technique designed to help managers in the planning and decision making. Programming problems are also known as optimization problems. The mathematical programming involves optimization of a certain function called objective function, subject to given conditions or restrictions known as constraints. Remember here, programming problems are also called as optimization problems, that is either the problem is to maximize or minimize. The mathematical programming involves optimization of certain function, that function is called as objective function, and the restrictions, that is subject to given conditions, are known as constraints. Here is meaning of LPP. Linear implies all the mathematical functions contain variable of index of most 1. Means here in all the equations the degree is 1. A LPP may be defined as the problem of maximizing or minimizing a linear function subject to linear constraints. These constraints may be equations or inequations. Now we discuss some terms related to linear programming problem. First term is decision variable. The variables involved in LPP are called decision variables. Second is objective function, a linear function of variables which is to be optimized, that is either maximized or minimized, is called an objective function. Third, constraints. Conditions under which the objective function is to be optimized are called constraints. These constraints are in the form of equations or in the form of inequations. Fourth, non-negativity constraints. In some situations, the values of the variables under consideration may be positive or 0 due to imposed constraints. Such constraints are referred as non-negativity constraints. For example, consider LPP as follows. Maximize z is equal to 65x plus 45y, it is our equation number first, subject to the conditions 2x plus y is less than or equal to 10, it is our equation number second. and 2x minus y greater than or equal to 2. It is our equation number 3rd. X is greater than or equal to 0. It is our equation number 4, and y is greater than or equal to 0. It is our equation number 5. In above LPP, x and y are called decision variables. The expression 1 is called objective function, that is z is equal to 65x plus 45y is called objective function. The expression 2nd and 3rd are called constraints, and the expression 4 and 5 are called non-negativity constraints. Remember here, equation 1 z is called objective function. In this equation, x and y are given, and that x and y are called decision variables. Subject to the conditions, here two conditions are given: 2x plus y less than or equal to 10 and 2x minus y is greater than or equal to 2. These two conditions are called constraints, and the conditions x is greater than or equal to 0 and y is greater than or equal to 0 are called non-negativity constraints. Now we see formal definitions related to LPP. First definition is solution of LPP: a set of values of the decision variables x1, x2, so on that xn, which satisfies the conditions of given linear programming problem is called a solution to that problem. Second definition is feasible solution: a solution which satisfies the given constraints is called feasible solution. Third definition is optimal feasible solution: a feasible solution which maximizes or minimizes the objective function as per the requirements is called an optimal feasible solution. Fourth one is feasible region: the common region determined by all the constraints of the LPP is called the feasible region. Now we see solution of LPP. There are two methods to find the solution of LPP. The first one is graphical method and the second one is simplex method. Note, we shall restrict ourselves to graphical method, means we use only graphical method. Here are some definitions. Solution: a set of values of the variables which satisfies all the constraints of the LPP is called solution of the LPP. Optimum feasible solution: a feasible solution which optimizes, that is either maximizes or minimizes the objective function of LPP is called optimum feasible solution. Here are two theorems without proof. Theorem first is the set of all feasible solutions of LPP is a convex set. And here is the second theorem: the objective function of LPP attains its optimum value, either maximum or minimum, at least at one of the vertices of convex polygon. This is known as convex polygon theorem. Students, to solve examples on LPP, we use corner point method. Here is the first step: convert all inequations of the constraints into equations. Second step is draw the lines in xy plane. Third step is locate common region indicated by the constraints. This common region is feasible region. Fourth step is find the vertices of the feasible region. Fifth step is find the value of the objective function z at all vertices of feasible region. Sixth step is determine which of these values is maximum or minimum, and the coordinates of these points are called optimal solutions. Students, remember all these steps to solve the problems on LPP. The problem on LPP is asked for 4 marks in board question paper. There is one case of solution of LPP, infinite number of optimal solutions. If the objective function has the same maximum or minimum value at 2 consecutive terms, say A and B, of the same feasible region, then the objective function has the extreme, that is maximum or minimum value at all the points of the segment AB. In this case, LPP has infinite number of optimum solution. Remember here, if the maximum or minimum is attains at 2 consecutive vertices of the convex set, then we say that in this case LPP has infinite number of optimum solutions. Now we solve some examples graphically on linear programming problems. Here is our first problem. Maximize z is equal to 9x plus 13y subject to 2x plus 3y less than or equal to 18, 2x plus y less than or equal to 10, x is greater than or equal to 0 and y is greater than or equal to 0. Here is the solution. To draw 2x plus 3y less than or equal to 18 and 2x plus y less than or equal to 10, we draw the lines 2x plus 3y is equal to 18 and 2x plus y is equal to 10. For that we prepare a table. Table consists of first column lines, second column its abscissa, third ordinate, fourth column line passes through the point, fifth column sign of the inequation, sixth column its region. Here first line is L1 is 2x plus 3y is equal to 18. To find the point of intersection with x axis and y axis, first we put x is equal to 0 to get point of intersection with y axis. When we put x is equal to 0, equation gives 3y is equal to 18. So, y is equal to 6. Therefore, point of intersection with y axis is 0, 6. Now, to find the point of intersection of the line with x axis, we put y is equal to 0. When we put y is equal to 0, we get 2x is equal to 18. Hence, we get the value of x as 9. Therefore, point of intersection with x axis is 9, 0. When we put x is equal to 0 and y is equal to 0 in LHS of inequation, we get 0 plus 0 which is equal to 0, and we know that 0 is less than 18. Hence, the region is origin side of line L1. Now, the second inequation is 2x plus y less than or equal to 10. The line L2 is 2x plus y is equal to 10. To find the point of intersection of this line with y axis and x axis, first we put x is equal to 0. When we put x is equal to 0, equation gives y is equal to 10. Hence, the point of intersection is 0, 10. To find the point of intersection with x axis, we put y is equal to 0. This equation gives 2x is equal to 10, hence x is equal to 5. Therefore, point of intersection is 5, 0 with x axis. Here the sign of inequality is less than or equal to when we put x is equal to 0 and y is equal to 0 in LHS of inequation second. So, we get 0 plus 0 which is equal to 0, and we know that 0 is less than 10. Hence, origin satisfies the inequation. Hence, the region is origin side of line L2. Students, remember x is greater than or equal to 0. For that, we draw the line x is equal to 0 and it is nothing but equation of y axis. And for y is greater than or equal to 0, we draw the line y is equal to 0, and we know that y is equal to 0 is equation of x axis. To draw the lines 2x plus 3y is equal to 18 and 2x plus y is equal to 10, first we draw xy plane. First we plot the point 0, 6. Since x coordinate is 0, so point is lies on y axis. Here is that point. Second, we plot the point 9, 0. Since y is 0, so that point is lies on x axis. Draw the line L1 passing through these 2 points. Now, we plot the point 0, 10. Here x is 0 and y is 10. So, that point is lies on y axis. Now, we plot the point 5, 0. Here y is 0. So, that point is lies on x axis. Draw the line L2 passing through these 2 points. Now, this is our common shaded region. Since x is greater than or equal to 0, y is greater than or equal to 0, and the region is origin side of the lines L1 and L2. So, this is our common region. Now, to find the point of intersection of these 2 lines L1 and L2, the line L1 is 2x plus 3y is equal to 18, and the line L2 is 2x plus y is equal to 10. When we subtract these 2 lines, then we get 2y is equal to 8, hence we get y is equal to 4. Put y is equal to 4 in equation second, therefore, we get 2x plus 4 is equal to 10. It gives 2x is equal to 6, therefore, x is equal to 3. Therefore, point of intersection of line L1 and L2 is 3, 4. The common shaded region OABCO is a feasible region with vertices O 0, 0, A 5, 0, B 3, 4 and C 0, 6. Now, these are vertices of feasible region. Now, we check the value of z at these vertices. For that, we prepare a table. Table consists of 2 columns. First one is for vertex and second one is for value of z. First vertex is 0, 0. Put x is equal to 0 and y is equal to 0. We get z is equal to 0. Now, for second vertex 5, 0. Put x is equal to 5 and y is equal to 0, we get z is equal to 45. For third vertex B 3, 4, put x is equal to 3 and y is equal to 4, we get z is equal to 79. And for the last vertex C 0, 6, put x is equal to 0 and y is equal to 6, we get z is equal to 78. Look at here in this table, here is maximum value, that maximum value is 79, which occurs at vertex B 3, 4. So, from the table maximum value of z is 79 and which occurs at the point B 3, 4, that is the maximum value of z is 79 when x is equal to 3 and y is equal to 4. Students, I hope you understood the examples on LPP. Thank you for watching the video till the end.